Energy is the lifeblood of the universe. It's the driving force behind every process, from the smallest atom to the largest galaxy. Understanding energy is key to understanding how the world works. In this journey through the fascinating world of thermochemistry, we'll explore the fundamental concepts governing energy conversions and their profound implications. Imagine the sun, a giant nuclear reactor in space, constantly radiating energy towards Earth. This energy, in the form of light and heat, fuels life as we know it. Plants convert sunlight into chemical energy through photosynthesis. We consume plants and animals, utilizing the stored energy to power our bodies. Every heartbeat, every breath, every thought, it all boils down to energy transformations. From the combustion of fuels that power our cars, to the chemical reactions that digest our food, thermochemistry helps us understand and control these energy conversions. It allows us to design more efficient engines, develop new energy sources, and even understand the intricate processes within living organisms. So, buckle up as we embark on this exciting adventure to unravel the mysteries of energy, its forms, and its transformations. Let's familiarize ourselves with the units of measurement used to quantify energy. We use specific units to express energy. The most common unit of energy is the joule, named after James Prescott Joule. A joule represents a small amount of energy. Lifting an apple 1 meter requires about 1 joule. For larger amounts, we use kilojoules, where 1 kilojoule equals 1,000 joules. Kilojoules are often found on food labels. Energy exists in many forms, constantly transforming from one to another. Two fundamental forms of energy are potential energy and kinetic energy. Potential energy is stored energy. Kinetic energy is the energy of motion. Energy cannot be created or destroyed, only converted from one form to another. Heat and temperature are often used interchangeably, but they have distinct meanings in thermochemistry. Understanding the difference is key to grasping energy flow. Temperature measures the average kinetic energy of particles. Imagine heating a pot of water. Heat increases the kinetic energy of water molecules. This rise in kinetic energy increases temperature. Heat is the transfer of thermal energy between systems. It flows from higher to lower temperature regions. Thermal equilibrium is when two systems reach the same temperature. The first law of thermodynamics, energy's unbreakable rule. Now let's dive into one of the most fundamental principles governing energy, the first law of thermodynamics. This law states that energy cannot be created or destroyed, only converted from one form to another. It's like the universe's ultimate accounting principle. Energy is always conserved. In simpler terms, the total energy of a closed system remains constant, even though energy may be transferred between the system and its surroundings or converted between different forms within the system. We can express the first law mathematically as du equals Q plus W, where du represents the change in internal energy of the system, Q represents the heat exchanged between the system and its surroundings, positive for heat absorbed by the system, negative for heat released by the system, and W represents the work done by or on the system, positive for work done by the system, negative for work done on the system. This equation tells us that the change in internal energy of a system is equal to the sum of the heat exchanged with its surroundings and the work done by or on the system. It's a powerful tool for understanding and quantifying energy changes in various processes. But first, are you enjoying the video so far? Subscribe so that you can ace that chemistry class and catch up on studying with the next videos. Now that that's out of the way, let's get back to the video. Exothermic versus endothermic reactions, heat flow and energy changes. Chemical reactions are all about the rearrangement of atoms and the breaking and forming of chemical bonds. These processes involve energy changes, often in the form of heat exchange with the surroundings. Exothermic reactions release heat into the surroundings, like a bonfire warming up a chilly night. In exothermic reactions, the products have lower potential energy than the reactants, and this energy difference is released as heat. The change in internal energy du for exothermic reactions is negative, indicating a decrease in the system's internal energy. Endothermic reactions, on the other hand, absorb heat from the surroundings, like a cold pack drawing heat from your skin to create a cooling sensation. In endothermic reactions, the products have higher potential energy than the reactants, and this energy difference is absorbed from the surroundings. The change in internal energy du for endothermic reactions is positive, indicating an increase in the system's internal energy. Understanding the distinction between exothermic and endothermic reactions is crucial in various fields, from designing efficient combustion engines to developing new materials and understanding biological processes. Measuring heat flow, specific heat capacity, and calorimetry. Imagine heating a pot of water on a stove. You notice that it takes a certain amount of heat to raise the water's temperature by a specific degree. This property, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, is called specific heat capacity. Specific heat capacity is a unique characteristic of each substance. Water, for example, has a relatively high specific heat capacity, meaning it can absorb or release a significant amount of heat without drastic temperature changes. This property makes water an excellent coolant and helps regulate Earth's climate. We can calculate the amount of heat, Q, absorbed or released by a substance using the following equation: Q equals msc dt. Or an easy way to think about it is Q equals mcat, where Q represents the heat absorbed or released in joules, Jm represents the mass of the substance in grams, Gc represents the specific heat capacity of the substance in J/G degree C, and dt represents the change in temperature, the difference of change, T final, T initial in degrees Celsius, degrees C, or Kelvin, K. Calorimetry is the experimental technique used to measure the heat absorbed or released during a chemical reaction or physical process. A calorimeter is an insulated device that minimizes heat exchange with the surroundings, allowing for accurate measurements of heat flow. Enthalpy, a deep dive into heat at constant pressure. In many chemical reactions, especially those occurring in open containers, the pressure remains constant throughout the process. In such cases, we use a thermodynamic quantity called enthalpy, or H, to describe the heat flow. Enthalpy is the sum of the internal energy of a system and the product of its pressure and volume. At constant pressure, the change in enthalpy, dH, is equal to the heat absorbed or released by the system, denoted as Qp. dH equals Qp. For exothermic reactions, dH is negative, indicating that heat is released to the surroundings. For endothermic reactions, dH is positive, indicating that heat is absorbed from the surroundings. Enthalpy is a useful concept because it allows us to determine the heat flow of a reaction without needing to measure the pressure and volume changes that might occur. Hess's law unlocking enthalpy changes in chemical reactions. Hess's law is a powerful tool in thermochemistry that allows us to determine the enthalpy change of a reaction without directly measuring it experimentally. It states that the overall enthalpy change of a reaction is equal to the sum of the enthalpy changes of its individual steps, regardless of the pathway taken. Think of it like taking a road trip. The total distance traveled remains the same whether you take the scenic route or the highway. Similarly, the overall enthalpy change of a reaction is independent of the intermediate steps involved. Hess's law is particularly useful when determining the enthalpy change for reactions that are difficult to study directly, or for reactions that occur in multiple steps. By breaking down a reaction into a series of known reactions with known enthalpy changes, we can calculate the overall enthalpy change using Hess's law. Calorimetry in action measuring heat flow in the lab. Calorimetry plays a crucial role in various fields, from determining the energy content of foods to studying the kinetics of chemical reactions and developing new materials. Let's take a closer look at a common type of calorimeter, the constant pressure calorimeter, often used in chemistry labs. A constant pressure calorimeter, also known as a coffee cup calorimeter, consists of two nested styrofoam cups with a lid, a thermometer, and a stirrer. The nested cups provide insulation to minimize heat exchange with the surroundings. To determine the heat absorbed or released during a reaction, we first measure the initial temperature of the reactants in the calorimeter. After the reaction takes place, we measure the final temperature of the products. By knowing the mass of the reactants, the specific heat capacity of the solution, and the temperature change, we can calculate the heat absorbed or released using the equation Q equals mc dt. Constant pressure calorimeters are relatively simple and inexpensive, making them a valuable tool for measuring enthalpy changes in various chemical reactions. Mastering thermochemistry, your key to understanding energy. From the units of energy to the laws governing its transformations, from the concepts of heat and enthalpy to the techniques of calorimetry, we've journeyed through the fascinating world of thermochemistry. Understanding these concepts is not just an academic exercise, it's about comprehending the driving force behind countless processes that shape our world. It's about appreciating the energy conversions that fuel our bodies, power our technologies, and drive the very dynamics of the universe. So, as you continue to explore the wonders of science, remember the power of thermochemistry, your key to unlocking the secrets of energy and its profound impact on the cosmos and our everyday lives. Have a nice night, and be sure to have a good night.